A powerful telescope has captured unprecedented and really beautiful images of the sun's surface, revealing sunspots and other features in new detail.
Hey there, space enthusiasts. Get ready to blast off into the cosmos with us. Welcome to Spaceverse, where the universe is our playground and curiosity knows no bounds. Join us on an interstellar adventure as we dive into the depths of space, uncovering its mysteries and marvels. From the secrets of black holes to the landscapes of alien worlds, we're here to ignite your imagination and expand your cosmic horizons. With mind-blowing visuals, expert insights, and the thrill of exploration, Spaceverse is your ticket to the ultimate cosmic journey. So strap in, hit that subscribe button, and let's embark on an epic voyage together into the vast unknown of Spaceverse. Due to the rising risk of solar flares, Sunspot AR3664 has swiftly become a key focus for scientific investigation. This enormous sunspot, one of the most active and largest of the current solar cycle, is now central to discussions about the potential impacts of space weather on Earth. Researchers and scientists are closely monitoring this sunspot, as its activities could have significant implications for our planet's technological and communication systems. In this video, we will examine the science behind this particular sunspot, compare it to historic solar events like the Carrington event of 1859, and consider the potential effects if a similar event occurred today. The Carrington event, known for causing widespread disruption to telegraph systems in the 19th century, serves as a benchmark for understanding the possible consequences of intense solar activity. By analyzing the characteristics and behaviors of Sunspot AR3664, we can gain insights into how such solar phenomena could impact modern society, which is heavily reliant on electronic devices and satellite communications. Sunspot AR3664 is far from ordinary. It's a massive feature, one of the largest and most active sunspots observed in this solar cycle. Spanning nearly 200,000 kilometers, it is more than 15 times the width of Earth. Its immense size and high activity levels have made it a focal point for both scientific research and public interest. The sheer scale of this sunspot makes it visible with basic eclipse glasses, allowing even amateur astronomers to observe it. This visibility has turned the AR3664 into a popular topic for educational and outreach initiatives, which aim to foster interest in solar physics and space weather. These programs often highlight the critical importance of understanding sunspots and their profound influence on various solar phenomena. Sunspots are fascinating regions on the sun's surface that appear darker and cooler than their surrounding areas. This contrast in temperature is primarily due to the intense magnetic activity occurring in these regions, which inhibits the convective processes that typically transport heat from the sun's interior to its surface. The magnetic fields within sunspots are incredibly powerful and complex. They can become twisted and sheared due to the dynamic and turbulent nature of the sun's plasma environment. This twisting and shearing of magnetic fields often lead to sudden and dramatic releases of energy, which manifest as solar flares. These solar flares are immense explosions on the sun's surface, releasing a tremendous amount of electromagnetic radiation across a wide spectrum, from radio waves to gamma rays. The implications of solar flares extend far beyond the sun itself. When these bursts of radiation are directed towards Earth, they can interact with our planet's magnetosphere, leading to a range of effects. One of the most significant impacts is the potential disruption of communication and navigation systems. For instance, solar flares can interfere with radio signals, affect satellite operations, and even disturb the functionality of GPS systems, which are crucial for modern navigation and various technological applications. Moreover, understanding sunspots and solar flares is not just about mitigating technological disruptions, it also has broader implications for understanding space weather and its effects on Earth's environment. For example, solar flares can enhance the auroras, creating spectacular displays of light in the polar regions, but they can also pose risks to astronauts and spacecraft due to increased radiation levels. In essence, the study of sunspots and their associated phenomena is a vital component of solar physics and space weather research. By closely monitoring and analyzing these solar activities, scientists can better predict and prepare for their potential impacts on Earth, ensuring the resilience and reliability of our technological infrastructure in the face of these powerful cosmic events. Sunspot AR3664 has been particularly prolific in producing solar flares, including multiple M-class and even X-class flares, which are among the most powerful eruptions. These events are not only fascinating to observe, but also crucial to study, as they can have direct impacts on our planet. The sunspot has also been associated with several coronal mass ejections, or CMEs, which occur when large bubbles of gas and magnetic fields are ejected from the sun's corona. Depending on their trajectory, these CMEs can collide with Earth's magnetic field, causing geomagnetic storms that can disrupt power grids and satellite operations. The recent activity of this sunspot demonstrates our star's significant potential to impact modern technology. This possibility for disruption highlights the necessity of closely monitoring sunspots like this one. Scientists utilize an array of tools, such as space-based observatories like NASA's Solar Dynamics Observatory and ground-based solar telescopes, to meticulously observe these features. By examining the growth, movement, and magnetic properties of this sunspot, researchers can better comprehend the processes that lead to solar flares and CMEs. This understanding is essential for enhancing space weather predictions, which helps safeguard satellites, power grids, and other critical infrastructure from the sun's erratic behavior. Globally, observatories and science centers are using this rare event to educate the public about the sun's dynamic nature and its effects on Earth. Projected images on sidewalks or screens allow even those without telescopes to observe this sunspot as it rotates with the sun and evolves over days. As we approach the peak of the sun's 11-year activity cycle, the insights gained from monitoring this sunspot are invaluable. Observing and studying it emphasizes the importance of these celestial phenomena and their profound impact on our technology-dependent world. The Carrington event of 1859, named after astronomer Richard Carrington, stands as the most potent geomagnetic storm on record. This event, triggered by a massive solar flare impacting Earth's magnetosphere, is pivotal for our modern understanding of solar activity, especially in the context of studying sunspots like AR3664. The similarities between the Carrington event and AR3664's recent behavior underscore the sun's capability to disrupt Earth's technological infrastructure. When Carrington observed the solar flare that now bears his name, the resulting geomagnetic storm reached Earth in less than 18 hours, highlighting the speed and severity of solar ejections. Telegraph systems across Europe and North America failed, with operators reporting sparks from their equipment, some severe enough to start fires. In the present day, AR3664 mimics this historical event, showing intense flares and CMEs that could cause similar or even more severe technological disruptions, given our increased reliance on electronic systems and satellites. In the aftermath of the Carrington event, auroras typically seen only near the poles were visible as far south as Cuba and as far north as Queensland, Australia, showcasing the powerful geomagnetic forces at play. With the AR3664's recent activity, scientists and researchers have ramped up their monitoring efforts, recognizing that vibrant auroras signify significant movements in Earth's geomagnetic field, which could herald broader electronic disturbances. The cultural and scientific significance of the Carrington event, which occurred in 1859, continues to resonate today as a crucial reference point for understanding and preparing for solar activity. This historic event has set a benchmark for what might be expected from significant solar storms, and its relevance is increasingly discussed in both academic and public spheres. In particular, Sunspot AR3664 has sparked numerous discussions due to its potential to cause disruptions comparable to the Carrington event, raising concerns about internet outages and widespread blackouts. Modern society's infrastructure is intricately designed and heavily dependent on stable magnetic conditions, making it particularly vulnerable to solar storms of the magnitude seen in 1859. The advancements in technology and our reliance on complex systems have increased this vulnerability. In response to the lessons learned from the Carrington event, various strategies have been developed over the years to mitigate these risks. These include hardening electrical grids, enhancing the resilience of satellite communications, and developing sophisticated early warning systems. International collaboration has been key in addressing these challenges. Organizations such as the United Nations Office for Outer Space Affairs and the International Space Weather Initiative have been at the forefront of efforts to improve global preparedness. They focus on enhancing the tools and methods necessary to predict and mitigate the impacts of space weather. These efforts include developing better models for forecasting solar activity, improving communication and coordination among countries, and investing in research to understand the mechanisms behind solar storms. Imagine the implications of a modern-day Carrington event. The consequences would extend far beyond beautiful auroral displays, potentially crippling the global economy and disrupting daily life on an unprecedented scale. This scenario isn't merely a theoretical concern, it's a real possibility given that Sunspot AR3664 continues to exhibit behavior reminiscent of the 1859 event. Today's society, with its intricate web of GPS satellites, power grids, and fiber optic cables, is far more dependent on technology than the world was in the 19th century. During the original Carrington event, telegraph systems, which were the most complex electrical technology in widespread use, experienced significant disruptions. The electrical currents induced by the solar storm were so strong that telegraph operators received electric shocks, and some telegraph systems continued to operate even after being disconnected from their power sources. In contrast, a similar event today could cause much more extensive damage. Power grids could be knocked offline, GPS systems could fail, and communication networks could be severely disrupted, leading to widespread chaos and significant economic losses. To address these potential threats, continuous efforts are being made to strengthen our infrastructure and improve our preparedness for such events. Advances in technology have allowed for the development of more robust and resilient systems, but the threat of a major solar storm remains a serious concern. Ongoing research and international cooperation are essential in ensuring that we are as prepared as possible to handle the impacts of a future Carrington-like event. Today, if a severe solar storm were to strike, the consequences could be dire and far-reaching. Such an event could result in widespread disruptions, knocking offline satellite communications and rendering GPS navigation unreliable. This would affect a multitude of services, from aviation and maritime operations to everyday smartphone usage. Furthermore, the power grid could be severely impacted, with the potential for regional or even global-scale failures. These power outages could last from several hours to weeks or even months, depending on the severity of the storm and the resilience of the affected infrastructure. The economic impact of a severe solar storm could be staggering. A study conducted by the National Academy of Sciences estimated that the cost to the North American economy alone could run into trillions of dollars. This figure includes the immediate expenses related to repairing and replacing damaged infrastructure, as well as the broader economic losses from prolonged outages and disruptions to businesses and daily life. The recovery times could extend over years, with certain sectors such as energy and telecommunications facing particularly long and costly restoration processes. In addition to the direct economic costs, there would also be significant indirect impacts. For instance, disruptions to communication and navigation systems could impede emergency response efforts, complicating the task of restoring normalcy. The financial markets could experience turbulence due to uncertainty and the potential for long-term economic slowdowns. Moreover, the social impact, with millions of people potentially left without power, communications, and essential services, could lead to widespread distress and instability. Given these potential risks, it is crucial to invest in research and preparedness to mitigate the effects of solar storms. Enhancing the resilience of power grids and satellite systems, improving forecasting models for space weather, and developing robust contingency plans are essential steps in safeguarding against the potentially catastrophic impacts of severe solar storms. By understanding and preparing for these events, we can better protect our technological infrastructure and economic stability in the face of such powerful natural phenomena. Apart from the economic repercussions, there are also significant human and environmental considerations to take into account. Vital systems like hospital equipment and water purification processes heavily rely on stable power supplies. A prolonged blackout could endanger healthcare services and access to safe drinking water. Despite these challenges, advancements since the 19th century have equipped us better to deal with such situations. Present-day researchers utilize sophisticated models to forecast solar activity and its potential impacts. Agencies such as NASA and NOAA manage fleets of observation satellites that provide crucial real-time data for early warning systems. At an international level, policies and protocols are being devised to respond to severe space weather events. To test the resilience of national and global infrastructure, simulations of large-scale solar storms are carried out. These endeavors are pivotal in constructing a response framework aimed at minimizing the chaos associated with a Carrington-level event. In conclusion, AR3664 serves as a stark reminder of the immense power of our star and underscores the significance of resilience and innovation in protecting our interconnected world. The study of AR3664 not only offers insights into the physics of our Sun, but also highlights our vulnerability to the formidable forces of our solar system. Through continual vigilance and scientific inquiry, we strive to ensure that if history were to repeat itself, we are far better prepared to confront its challenges than ever before. And that's it. Thank you for joining us on this exploration of the dynamic and potentially disruptive world of Sunspot AR3664. By comprehending these powerful solar phenomena, we can enhance our readiness for their impacts and safeguard our technology-driven society. Keep watching the skies and remain curious about the wonders of our solar system.